We shall begin. Today we're gonna pick up where we Today we're going to pick up where we left off last time. Last time we introduced and derived the point reactor kinetics equations. Today we are going to talk more about them, about their solutions, and how we can use the understanding of those solutions to better predict how reactors will behave as functions of time during different kinds of transients. And we'll also talk a bit more about what does it mean to have a transient and how do what aspects of our reactor system could be influenced by um, could be changed, which would cause the time dependence of our system to change. Before I got into talking about the content, I wanted to talk about the exams. Um, I finished grading the exams over the weekend. Those grades are on Canvas. This is the distribution, like the histogram of the exam scores after the curve. So in general, when I taught this last year, I didn't curve any of the exams. This year's scores were less than last year's by quite a bit. Like the average was about like 15 to 20 points lower than it was last year. And I've taught the class pretty much the same way as I did last time. The biggest structural difference with the class is that last time I had a grader who was able to grade the problem sets. So instead of the problem sets being like optional, the problem sets were given as an actual assignment, which that's the way that I would prefer the class to be set up. I think it's unfortunate that the department doesn't give me a grader for this class because there's not enough people in the class basically. So like that's the reason that I haven't assigned the homework. I think that practice is the way that you learn. And I think that from a student perspective, it's nice to have that practice be incentivized by the fact that, like, if the homework was actually a grade. So I think, so I mean, this is the distribution. These are some of the statistics, and these are the statistics after the curve. So, like, before the curve, the highest score was a 79. And so the way that I curved it is I made that 79 become I turned that 79 into a 100, which means I added 21 points to that highest score. And then I took that 21 and I added it to all of the other scores. So when you're seeing your grade on Canvas, that's the grade, including that plus 21 point curve. Um, when you get your exam back, and I'll pass them back at the end of class because I want us to be focused on the lecture. And then after class, I'll pass the exams back. And if you have any questions about those exams, about the scoring or anything like that, then we could talk about it then. But I think once you get the exams back, if you compare those questions to the questions that were given on the problem sets, I think you would agree that the questions are fair. And when I say fair, like an exam question being fair, meaning that like it's not far off from what you would have been asked to demonstrate like on a problem set. Um, and also like mostly those questions are coming from the problem set questions as well as when we did the review and I gave the list of derivations, I just picked one of those derivations out to be the one that showed up on the exam. So I think that's the other aspect of it is like making sure like some of the questions that I was seeing, like if I was seeing a question that was given as a problem set question and it's like basically blank, or we're writing things down for that problem that like don't really have any bearing on what the question was actually asking, to me, that's evidence of us not doing the problem sets or maybe not doing them in a way that we're actually learning from them. And there's a variety of reasons why that could be. So I basically just wanted to make the point to like in terms of these scores, the first exam does not like make or break your grade for the class, and I'll talk about that on the next slide. But just in terms of like doing better, because I'm sure we all want to do better than we did on the first one, the most important thing is that you're doing those problem sets, that you're doing them yourself, that you are actually working through and maybe struggling with them a little bit because you want to struggle in the time when you don't have like a time limit necessarily. Like if you get that problem set, you basically have a week to do it. And if you're not struggling when you're actually trying to learn it for the first time, then you're going to see those questions on the exam, and you're not going to have built the muscle memory for being able to do them effectively and efficiently, which means that you're going to end up struggling more on the exam than you would have if you had done all the problem sets, done them yourself, and like really made sure that you understood them. So when I give those problem sets, make sure that you're starting them as soon as you can. Make sure that if you have questions about them, you're asking those questions. Um, Make sure that you're using the class notes as your reference, like primary sources versus like non-primary sources. In this class, the primary source is Dr. Svetkov's notes, but it's also like our lectures. As I was going through the exam and I was looking at some of the questions that were given, I just got curious and I was asking myself, like, what does Gemini say about some of these things? And sometimes Gemini gives crazy, like wildly off answers for stuff. And so if when you do get stuck, you're using like an LLM as your first source of trying to understand it, you're gonna possibly be led astray. Whereas if you look for those things in the notes, Dr. Steinkopp's notes are really complete. They're very detailed, but almost everything that I ask, you can either find in his notes as like the figures that I was asking for sketches of. Those figures are all in Dr. Svedkov's notes. So like the first thing, if you're trying to find something in the if you're trying to figure out if something is in the notes, I would like open that PDF that I gave y'all and I would just control F for keywords. And if you do that, you can find a lot of that stuff in the notes and you don't even have to use ChatGPT. To the extent that you are using like an LLM, that's a lot more helpful if you've already like if you have the problem, you've already tried a couple things and you're still stuck, putting in like a detailed prompt where it's like, here's my problem. Here are the things that I've tried. I'm still getting stuck. Can you help me better understand where I'm going wrong? That kind of approach to like going with these large language models is a lot more effective because you're basically doing kind of what you would do if you like came to a tutoring session. Whereas if you just like paste the question in and then like take the answer as like a, gold standard, then chances are you might end up like learning something that's actually incorrect because these models don't learn and they don't know anything. All that they do is they take your prompt and then they try to figure out what's the statistically next likely string of words that would be a response to that prompt based on all of the text that they've been trained on. So they don't know anything, and chances are they haven't been trained on Dr. Svedkov's notes. So if you get asked a question that's very specific and phrased in the context of what Dr. Svedkov has in his notes, it's going to give you something. It's going to be very confidently wrong about the thing that it's giving you, and then you might be led astray. Whereas if you use the notes as a primary source and also use me as your primary source, like when you have questions, ask me. I'm very happy and eager to help explain things and to help you guys understand. I want you guys to learn. And so, yeah, making sure you're doing those things. Similar with the derivations, like most of those derivations are in Dr. Svetkov's notes. So the first thing that you would want to do is just use the notes to kind of walk through that derivation yourself. And then when you're practicing for the exam, like I've had in grad school, I've had exams that are all derivations, but usually you get a list of like 10 derivations and then if you know that those are the 10 that you might see, like you might see 3 or 4 out of those, then I just grind on understanding and like practicing those derivations. I try to get myself to the point where I could do every single one of those derivations just looking at the problem statement and not using my notes at all, because that's what you're going to have to do on the exam. If you get a derivation, you're not going to have notes to look at. You're going to need to have really internalized the process. And if you work through them first and then you practice going through them from scratch, that's going to be the best way, I think, to make sure that when you see something on the exam, that you're not getting surprised by it. So hopefully that makes sense. I wanted to just remind us about how the grades are like kind of distributed in the class, which is that for every like course element, there's not like a fixed weight. It's kind of like a range of weights. And so like for example, what this means is that like if you don't do well on exam one and you don't do well on the quizzes, then you might be looking at your grade and being like, I'm cooked. I'm not going to be able to pass. I might as well just give up now. And that's not the case. It's very much still recoverable. So like this is an example of a student who maybe has a 45 on exam one and has a 50% for the quizzes. So those two things being like the lower grades would get the lowest possible weight. The quizzes would get a weight of 10%, exam one would get a weight of 15%. And then after that first couple of assignments came out, they reflected, they improved on their studying processes, and they did improvement throughout the course. Then even if they were to end up with like a 70 on exam two and an 80 on the project and an 80 on the final, they would end up passing the class. So like don't look at your score and think of it as something that's like set in stone. Think of this from like a growth mindset of like I'm not done yet. There's still like a lot of more grade to come. And if I messed up on something, like that's okay. Everybody makes mistakes. I've failed classes before, so like I know how it is. Um, and when you mess up on something, you can either give up or you can say, I'm going to learn from my mistakes. I'm going to do better the next time. And so that's what like the growth mindset is all about. So I hope that even if the exam didn't go how we were planning it to go, that we realize that we can still course correct and we can still improve and we can still like do well in the course. But it's time to lock in if we are if because right these are like the grades that you would need to pass. So if these grades ended up being any lower, then like it's going to be a struggle. So this is the time to lock in and to make sure that we're staying on top of our stuff and that we're improving. And so I'm going to start doing those weekly homework help sessions. I'm going to do them on Tuesdays. I have sent the email out to the to, uh, I've sent the email out to get that room reserved. So I'm just waiting to hear back on what room is available. Um, if I don't get a room reserved, then we'll just make that first session be in the Nuke Lounge, and then once I know about the actual room, then I'll let you guys know. So tentatively, we'll plan for Tuesday, which would be tomorrow, from noon to one in the Nuke Lounge, unless I'll send out an email either way. But yeah, that's the plan. So hopefully that is a helpful thing for us so that we have like detailed time where we can work on these things together. If you have specific questions, or if you want to just like, if you want me to work through examples or help walk y'all through examples, that'll be time for you guys to ask the questions that you're struggling on. So be very student focused on getting questions answered so that we can make sure that we're understanding those problem sets and that we're also like if we need help with the reactor design project or if we need help preparing for the exams, that'll be a helpful thing for us. And hopefully that'll help kind of alleviate some of the questions that we've had or some of the uncertainties about not maybe knowing how to do certain things. So hopefully that's okay. Hopefully that makes sense. And with that being said, let us move forward. No, I'm not going to give a key. When you get the exam back, I gave a lot of feedback on the exam. Um, so but because a lot of those questions either come from the problem sets or from the like derivations in the notes, like the derivation is all spelled out in Dr. Svedkov's notes. So like the key is kind of already there. And if you have specific questions about the exam questions that like maybe aren't uh, given answers in the problem sets or in Dr. Svedkov's notes, we can definitely talk about those things. But yeah, once you see that's a good point though, is like once you get that exam, you want to review the things that you made mistakes on and you want to like try to get the correct solutions for those things because it might not show up on exam two, but those things could show up on the final because the final will be cumulative. So if you did mess up on things on the first exam, you don't want to just like put that out of your mind. You want to make sure that you're going through the work of fixing up on those things because you might see them again. Um, so any other questions about any of that before we move forward? All right. So last time we started talking about time dependence, and the main thing that was affecting our like discussion about time dependence was that we hadn't separated the prompt neutrons, which come immediately out of fission, from the delayed neutrons, which come out of fission from the decay of fission products that might be seconds or minutes later from the fission event. Um, So we talked about delayed neutrons. We mentioned that they come from delayed neutron precursors, which are the fission products that emit these delayed neutrons. And then we took our energy dependent diffusion equation and we modified it so that we had a source term for delayed neutrons. And we also modified our fission production term such that this the number of neutrons per fission here is only talking about the number of neutrons coming out of a prompt fission. So we're kind of separating the prompt fission component from the delayed fission component. And this equation is a balance equation. It's an energy dependent balance equation. So it basically says the rate of change of my energy dependent neutron density equals all of the ways that my density could be removed. And that's equal to all the ways that my density could increase. So it's change rate. In this case, it's plus my loss rates equals my gain rates. And each term in this equation is an energy dependent neutron density. So it has units of neutrons per unit volume, per unit time, and per unit energy. Um, that source term was the thing that we were trying to come up with an equation for. So we introduced some definitions. We introduced the precursor concentration. This would be the density of our type I delayed neutron precursors at some time t. So it's a density that has density units. We introduced the decay constant for those type I delayed neutron precursors. This is a probability per unit time that that delayed neutron precursor will decay. And when that delayed neutron precursor decays, that's where the delayed neutrons come from. Um, and we introduced an energy spectrum for the neutrons that come out of delayed neutron precursors because the fission process is different from the decay process. So you have a different energy spectrum describing the energy of the neutrons that come out of these decays, which is distinct from the energy of the neutrons that come out of fissions. And then we realized that if we multiply these three quantities together, that gives us a energy dependent neutron density. It basically tells a neutron rate density. So it basically tells us the number of delayed neutrons per unit volume, per unit time, and per unit energy that are coming from our delayed neutron precursors. And then we said, okay, well, now we're still kind of stuck because the CI, this precursor density, is another unknown. And so we need an equation for those precursor densities. And we use conservation for that. We said, okay, this precursor constant, these precursors are another substance that I could track in my reactor. And I could track them by saying the rate of change of those precursors equals the ways that they're gained minus the ways that they're lost. And for these precursors, they're come about because of fission events. Like every fission reaction is going to produce some fission products that could decay and produce these delayed neutron precursors. So the gains of these precursors is due to fission. And then the losses are because these delayed neutron precursors are radioactive, they decay. And so the losses are due to their decay rate. And then the only other thing that we introduced to set up our balance equation was we defined a new for delayed neutron precursors of type I. And this is technically the number of delayed neutron precursors that come out of fission. But then we made the argument that because every delayed neutron precursor that we're tracking is going to produce exactly one delayed neutron, then we can kind of think of this as basically the number of delayed neutrons that come out of a precursor of type I when it was caused by a fission of a neutron with an energy E. So from there, we wrote our precursor conservation statement. The rate of change of those precursors equals the gain rate, which looks awful lot like a fission production rate, but just with a nu for delayed neutrons instead of a nu for like all fissions. And then the loss is due to the decay rate, which is the lambda times the concentration. And so then we wrote our energy dependent diffusion equation as a coupled set of equations where we had that precursor term spelled out, and then we had our equations for each of those precursor densities. And then basically what we did was we took those equations and we turned them into the point reactor kinetics equations. We made the assumption that the medium was infinite, which knocked out that leakage term. We assumed that it was a homogeneous medium, which meant that we didn't have to write any position arguments on any of like our cross sections or our fluxes. We took those equations and then we integrated them all from 0 to infinity to kind of turn it from an energy dependent problem to basically get rid of the energy dependence. That allowed us to simplify things a lot because a lot of those terms contain probability density functions in energy. And when we integrated them over 0 to infinity, a lot of those probability density functions turned to 1. And then we rewrote, instead of having the energy dependent flux, we rewrote it as an energy dependent neutron density times the neutron speed. And then we use some prior definitions that we had seen, like if you take that energy dependent neutron density and integrate it over all energies, that just gives you the regular old neutron density, which relates to the regular old scalar flux. And we also use the definition for the average of a function to take some complicated looking integrals, multiply them top and bottom by something, and then converted those and then recognize the form of an average to get some average quantities in our equations. And then we defined a couple other terms that allowed us to take those resulting equations and then convert them into the point reactor kinetics equations. So we defined the delayed neutron fraction, which is beta with a bar on top. And that's basically, as the name suggests, it's the fraction of our fission neutrons that are born delayed. So it's basically the number of delayed neutrons coming out for fission per fission divided by the total number of neutrons coming out per fission. We defined this LP, the fancy L with the P is the prompt neutron lifetime, which has units of seconds and basically tells us how long a prompt neutron exists in our reactor from when it's born to when it gets absorbed by something. We introduced the definition of the reactivity, which is kind of like just another way of recasting the multiplication factor. We defined the mean generation time, which is LP over K. And this is basically the average amount of time that it takes one that from so if we have like one generation of neutrons and then we say how long does it take for that next generation of neutrons to come about, that's what that mean generation time is. It's the time between successive generations of neutrons. And then we introduced the delayed neutron fraction beta I, which is the delayed neutron fraction for some type I delayed neutron precursor. So that looks like the number of neutrons coming out delayed from that delayed neutron precursor divided by the number of neutrons that are from coming out from fission, from all fissions. Good question. So those brackets mean an average. So it's like an average of that quantity inside of the brackets. It's with an average, you can either write like a function with an overbar, and that's equivalent to writing something like that. So yeah, and then in that case, it's an average of that quantity F. And then we put all that stuff together to derive the point reactor kinetics equations. So that was kind of how we got here. These equations are really useful. They're one of the most useful models that we have in this class. And in this case, they're a useful model for understanding how do reactors respond as functions of time when you have various reactivity insertions or removals from your reactor. Um, when we say point kinetics, it doesn't mean that the reactor is a point. To get these, we actually assume that the reactor was infinite. It assumes that the flux doesn't have a shape that changes with time. And in problem set 5, there's a kind of alternative derivation of the point reactor kinetics equations. And so you'll see kind of where that name comes from if you take a look at that derivation in problem set 5. All of these quantities that appear in here, like rho and beta and big lambda, those all kind of depend on my neutron population. So they themselves are usually time dependent, but we can treat them as constants and be able to, that allows us to be able to do analytical calculations with these point kinetics equations that end up being very useful for understanding time dependence. And that's going to be our goal for today. When we think about these point reactor kinetics equations, they are a coupled system because, like, if we're trying to find the neutron density from equation 1, it depends on itself, but it also depends on those precursor densities. And then I have a precursor density equation, but it also depends on the neutron density itself. So the N total and the CI appear in both equations, which makes them coupled sets of equations. I only have one equation here for the basically the my neutron density equation. There's just one of them. But then for this precursor density equation, there's capital I of them depending on however many delayed neutron precursor groups I have. Like if I have six delayed neutron precursor groups, then little I will go from one all the way up to six. So I would write this equation out for each of those groups. I would have an equation for C1, C2, C3, all the way up to C big I. So I have big I numbers of these equations. This is basically the number of equations I get from this, and this is the number of equations I get from that. So they're a coupled system of I plus 1, and these kinds of equations are ordinary differential equations. So a coupled set of I plus 1 ordinary differential equations. And our goal for today is going to be to try to figure out how we can solve. Oh yeah, what's up? So the point of Fourier transformation. Mhm. How how does that assumption work? The expression function in practice, the way that it works is that it's kind of only valid for like the first early stage of the transient. So it's like we can have, and we'll talk about this later, but we have like different scales of time scales over which we talk about these things. The point reactor kinetics equations are really most accurate for like the very short term time scale because over the short term, we can assume that that flux shape doesn't vary with time very much over like a short time scale. And then over longer time scales, we can make some corrections to the point kinetics equations to make them more accurate for slightly longer time scales. And then for the longest time scales, we can't really use the point kinetics equations, and we have to have other sets of equations that will help us do things more accurately. So yeah, it's a good question, and I think hopefully as we get a little bit into the lecture, it'll kind of make more sense. So I wanted to help us understand some of the terms that are in those equations a little bit more. So we have big lambda, which is the mean generation time, which is like the average time that it takes for one generation of neutrons to go to the next generation. And because of the definition of the mean generation time, you can kind of rewrite this equation in terms of K effective being the prompt time over the mean generation time. And based on this definition, we can write our criticality conditions based on how these parameters vary. So for example, if we're subcritical, which means K effective is less than 1, it means that big lambda is bigger than the prompt neutron lifetime. So big lambda is bigger than LP would be corresponding to a subcritical configuration. If these quantities are exactly equal, then K effective would be 1, which would be critical. So if big lambda is equal to the prompt neutron lifetime, then it's a critical configuration. And then supercritical would mean that the prompt lifetime is bigger than the mean generation time. So if the prompt neutron lifetime is bigger than the mean generation time, then that would be a supercritical configuration. And like I think hopefully that kind of makes sense that if the time that it takes, if the time that a neutron is alive in your reactor is exactly equal to the time that it takes for a new generation to be born, that means that your system is in perfect balance. And if your prompt lifetime is longer than the mean generation time, it means that those neutrons are surviving in your reactor for longer than it takes for a new generation to be born, which would mean that the population would steadily increase. And then kind of opposite, that if your prompt lifetime is less than the mean generation time, then these neutrons are only living in the reactor for less time than it actually takes for them to be born. And that means that over time, your population is going to decrease. The other thing I wanted to talk about was the reactivity, which is rho. And it's an unfortunate thing because in nuclear engineering, you'll see rho for the atom density, in which case that rho is the mass density of the material that you're finding the atom density of. And so if you see rho in any other context, it's probably talking about a reactivity. Sorry that we have to use the same symbol for different quantities. But yeah, if you see rho outside of like an atom density, it's probably a reactivity. By definition, the reactivity is like a measure of how far you're deviating from a critical configuration. So what it means is that we can talk about our criticality conditions in terms of the reactivity instead of the multiplication factor. So like if we were critical, that means k equals 1. And so if I put a 1 here, then I'm going to have 1 minus 1, which would be 0. So a critical configuration corresponds to a reactivity of 0. And if we're supercritical, that means k is greater than 1. So like maybe k is like 1.1. So we've got like 1.1 minus 1 over 1.1. That means that the reactivity is going to be some positive number, some number greater than 0. So if we're supercritical, it means that reactivity is positive. And then opposite, if we're subcritical, that means k is less than 1, like maybe k is zero point 0.9. So we'd have like zero point 0.9 minus 1, which would give us a negative number. So if we're subcritical, it means that the reactivity is negative. And so that's what we mean when we say that that reactivity is a deviation from criticality. Because if you're exactly critical, rho is 0. And then if you're above critical, supercritical, then rho is some positive number. And if you're below critical, then rho is some negative. So this is where I just kind of wanted us to be aware of slight different notations from the way that we've talked about things so far to what they look like in Dr. Svedkov's notes. And in Dr. Svedkov's notes, when he's writing these like the point reactor kinetics equations, he's writing them in a very detailed form that's a lot more general than the way that we've introduced it so far. So like there's three different kind of indexes that he is talking about. There's an I index, which is the same I that we're using, the number of delayed neutron precursor groups. There's also a little g, which is the group index, which is also the same way that we've talked about it, but we just haven't talked about energy dependence and we haven't done like a multi-group point kinetics expression. So we haven't really talked about different energy groups. But then he also adds this index little j, which is talking about the number of fissionable nuclides. So like um, this is a table that comes out of those notes where we're getting values of the number of neutrons that are emitted for number of delayed neutrons per fission, which is the nu with the FD, the number of total neutrons per fission, which is the nu F, and then the delayed neutron fraction. And this is for all these different kinds of fuel types. So that little J is just an index that reminds us that like in a reactor, you might have uranium and plutonium and americium all in your reactor. They are going to have slightly different numbers of neutrons per fission. They're going to have slightly different delayed neutron fractions. And so that J is just a way that we can keep track of multiple different fissionable nuclides. And if you notice from this table, the definition of the beta J, the delayed neutron fraction for some fissionable nuclide J, the is just the nu FD for that isotope. So nu FD for that isotope J divided by nu F for that isotope J. Bless you. So that's just a definition that is kind of by the definition of the delayed neutron fraction. That's how this column is coming about. Um, so yeah, this is an interesting table to be aware of. It might be a useful one too when you're looking at the problem sets and you're given a certain fuel type and you're using the delayed neutron, you're using the point kinetics equations. If the values aren't given, this would be the table that you could jump to define various parameters that might be useful for solving those problems. And like you do not have to memorize these. If I was giving you like an exam question that required using these things, I would give you the table, but it's just good to be aware of that table existing and where to find it and what information you would be pulling out of it. So in terms of talking about our precursors, We had already mentioned that there's a lot of precursors. There's like over 200 that have been identified, but we don't keep track of all of them. In fact, we only have to keep track of like about a couple dozen of them. And because those are the only ones that have time scales, time constants over which like we really need to worry about them. And so in general, that we care about the delayed neutron precursors that have short half-lives. So we care about the delayed neutron precursors with half-lives that are small. And that would mean on the order of seconds to minutes. On the order of seconds to minutes. Because if the delayed neutron precursors have really, really long half-lives, that means it takes them a really, really long time to decay, to produce new delayed neutrons. And if the time that it takes for that to happen is like a lot longer than the mean generation time, then they kind of end up being negligible in terms of their impact. So that means that we don't have to keep track of all 270. We can ignore a lot of them. And what we can also do is group a lot of them together, like precursors that have similar half-lives. We can group all of those together. So that's what we mean when we say delayed neutron precursor groups, is that like we might be taking like 5 or 6 nuclides that are delayed neutron precursors that all have similar half-lives and just lumping all of those together. And in general, the most common number that we use is 6. We usually use, sorry, that's supposed to be a 6 DNP groups. And so that would mean our big I goes up to 6. And for each group of delayed neutron precursors, we can characterize a decay constant for that group and an abundance for that group. Um, and by definition, the decay constant is equal to the natural log of 2 divided by the half-life. And then this would be, so we're talking about for this precursor I coming out of some fissionable nuclide J. So let me just make that J a little bit better. Half-life for some precursor I that's born from some fissile nuclide J. And then the abundance, the relative group abundance, is my beta I divided by the beta effective. Um, and so, yeah. And that beta, the overall beta effective, is basically just the summation of all of the individual beta I's. So we can use these definitions to characterize our different groups. If those groups end up being kind of lumped together based on having similar half-lives, which kind of ends up meaning that they have similar decay constants. So if you wanted to, you could take a big set of delayed neutron precursor groups and you could lump them all together to just have one effective delayed neutron precursor group. And these are the corresponding ways that you would get those equations. These are the equations you would use to do that summing or that averaging. So notice like if you see a subscript I on these quantities, it means that that is that quantity for a particular delayed neutron precursor group. And if you don't see the I, that means that it's an effective value that has kind of been comes about by summing up or averaging the values from all of the other precursor groups. So like my effective delayed neutron fraction, beta, is the sum of all of my individual beta i's. And then based on and it can be useful to have the beta over lambda, which is basically just summing up the individual betas over lambdas for all of my different groups. Um, we can kind of rearrange this equation to put the beta on the other side, the overall beta. We can take that overall beta and throw it inside of this sum, and then inside of the sum we'll have a beta I over big beta, and that by definition is the abundance. So that's how you could find the overall decay constant for one group, for an effective group, knowing the abundances of each group and knowing the decay constants of each group. And this is another useful table that is in Dr. Svedkov's notes that talks about 3 different nuclides for a six precursor group model. So I goes from one to six, and then we have the abundances for each group, and we have the decay constants for each group. And then the subscript J just reminds us that these are the values that belong to the isotope U-235. These are the ones that belong to 241, and so on. And these decay constants in this table all have units of inverse seconds. So yeah, that's just the units aren't there, but lambda I does have units of inverse seconds, whereas the abundance is just a ratio, so it doesn't have any units. So in general, as nuclear engineers, we want to look at a reactor and we want to be able to predict how that reactor is going to respond as a function of time in a variety of different situations that could make my reactor go from critical to some deviation from critical. So when we talk about reactor kinetics, what that means is that we're modeling the time dependence of the neutron population. So kinetics in general is talking about modeling a time dependent neutron population, which is what we're doing right now. And that is kind of distinct from reactor dynamics, which involves kinetics. So we're considering the time dependence of the neutron population, but we're considering that with kind of extra physics built in, mostly talking about temperature and control feedback. And we'll talk more about feedback in the upcoming lecture, but I just wanted to kind of set the stage for that by realizing that kinetics and dynamics in this context are slightly different. And we'll see more about how a lot of our quantities in nuclear engineering are functions of temperature, which means that temperature of our reactor influences how our reactor behaves. And also, our reactors are complicated systems that have lots of control systems. There's all this instrumentation and control that, like, in your reactor, you might be monitoring a lot of different variables. Like you'll be monitoring your flow rate, you'll be monitoring your power, you'll be monitoring your flux, you'll be monitoring your temperature. And you have all these control systems which are constantly recording and looking at those values and then making different changes based on how those values change. Like you might have a control system that says, if my flux goes above a certain value, scram the reactor so that it doesn't blow up or so that things don't melt down. And we'll talk more about that when we get into feedback. In general, these reactors are complicated kind of systems. So you can think of them as like a bunch of connected components that are all working together and interfacing with each other and influencing each other. And for each of these various systems, like my reactor core and my heat exchanger and the fluid flow through my reactor, you have like kind of governing equations that you can use to describe that system to predict various aspects of the system. Like for a reactor core, we might be interested in solving the energy dependent diffusion equation, and that would tell us information about our flux. It'll tell us about, if we could solve that equation, it'll tell us about our energy dependent neutron flux, which is the flux that can vary with energy, with position, and with time. If you're in heat transfer and you're doing heat diffusion, like that big heat diffusion equation, that ends up being useful so that you can get the temperature distribution in your reactor. So getting your temperature as a function of position and as a function of time. If you solve the Navier-Stokes equation, then you could get your velocity distribution as a function of position and time. So you have lots of different governing equations that correspond to different parts of your system. And these things ultimately end up being coupled to each other. Like the temperature in my system is going to influence my flux because of how cross sections change with energy. The flow distribution of my system will affect the flux because the flow distribution will affect the temperature distribution. And so all of these things are kind of complicated and interdependent. And so we really need to know a lot about a system if we want to model the dynamics in detail. So in terms of being in a critical state, which is like most of what we talked about in this class. We've mostly studied critical reactors in various shapes, in various contexts. And we know that critical just means that the population is balanced, that the gain mechanisms and the loss mechanisms of our system are balanced out. And that also means, and in consequence of that, it means that our system is in a steady state. So it means nothing is changing with time. Um, can a reactor be in steady state forever? Can it be critical forever? No, it cannot. And so the answer, of course, is no. And like, even if you had a critical reactor and you just kind of left it going, at some point the fuel is going to burn up and then you're going to end up going subcritical. And so there's lots of other things that could happen to our system that would make it deviate from critical. And if you are critical and you deviate from critical, you kind of only have two ways that you could go. You could go above critical or you could go below critical. So you can only move in two directions. You could either go supercritical, meaning that your reactivity goes above, or your multiplication factor goes above one, or you could be subcritical, which means that your K goes below one. And when we talk about a transient, that is just something that has happened to our reactor that's changed the state of the reactor. And so, as nuclear engineers, we need to be aware of all of the different things that might change the reactor state, because that is going to make us go away from critical. And in some cases, it might make us go below critical, but in some cases, it might make us go above critical. And then we need to be aware of those things so that we can mitigate them and so that we can know also about how different things happen over different time scales. And if we know those things, then we have a better understanding of how to design a reactor and how to make it safe in all of the different kinds of circumstances it could find itself in. So these are just some of the various things that could influence our reactor state. When we talk about fuel burnup, that's like the consumption of the fissile material in our core. That if you have some enrichment of U-235 of your fuel when you put it in, as the fuel fissions, that enrichment is very slowly decreasing. So as a result of fuel burnup, the reactivity of your fuel goes down. But also, some of the fuel in our reactor, like uranium-238, can absorb a neutron and then go through a transmutation process where it becomes plutonium-239. And plutonium-239 is also fissile. So you can also end up building up new fuel nuclides as the reactor operates. So in that sense, burnup can reduce your reactivity or increase your reactivity depending on how things are going. And those changes in our fuel composition will change K effective, which will make us deviate from criticality. Um, Fission product buildup and decay is really important, especially for longer time scales, because some of our fission products will decay and they will become isotopes that are really strong neutron absorbers. Xenon 135 is an example of that. And if you end up producing these really strong neutron absorbers, that's going to affect the absorption characteristics of your system, which will affect the multiplication of your system. Temperature can change our reactor state and can affect our criticality because material properties end up being temperature dependent. Like the density is a function of temperature. So as you heat something up, it expands, which affects the density. That ends up feeding into the cross section because the macro cross section depends on the density and the micro cross section. So increasing temperature ends up decreasing your density. It also ends up affecting your cross sections, which affect your number densities, and your cross sections, which affects your reaction rates. And also the power level of our reactor affects the temperature too. So all of those things can influence K effective, the geometry of our system, and also any material changes to our system. Like if we insert a control rod into our reactor, that is changing the material kind of makeup of our core, which is going to change the absorption characteristics, which will change K effective. And the reverse is true too. If you just like remove a control rod really quickly from the reactor, then you're reducing the absorption, which is probably going to could make your reactor go supercritical. Environmental changes, like reactors are coupled to and influenced by the environment. Like almost every reactor that you see is built near a lake or near like a large body of water because that ends up being like the ultimate heat sink. And this is actually a more current example might be in France. In France, some of the rivers are getting so hot that they're having to shut their reactors down because of the fact that the heat from the reactor goes into the river, which could make things get even hotter. So there's certain like environmental limits on the reactors and how hot the water reservoir that they're attached to can go. So environmental factors. In 2021, when we had that crazy winter storm, the South Texas project had to turn its reactors off too because their big pipes that take coolant from one reservoir to the reactor, the pipes literally froze. And so it was so cold that they had to turn the reactors off because of the fact that things got frozen. And then accidents can also affect your reactor systems, which could affect how the reactor operates. So, like with Fukushima, there was that big tidal wave. That tidal wave was so large that it went over their seawall. And then they had these backup diesel generators, which their offsite power got knocked out because of the earthquake. And then they had these backup diesel generators that got flooded. And so that was an example of an accident damaging the system components, which meant that you had no power to keep running water through the reactor core to keep things cool, and then the reactor had a meltdown. So lots of different things can change the reactor state. We want to be aware of those things, and we also want to be aware of some of the time scales over which those things take place. And so general, we have three kind of cases of time scales. We got short time, intermediate time, and long time. Short time meaning like seconds to minutes. Whoops. And over seconds to minutes, we're mostly just concerned with like any accident or any action that might quickly change the system. And those will generally be described as transients, like the removal of a control rod or the trip of a pump. And in those short time scales, we can assume that the reactor flux shape doesn't change that much with time. And that means that the point kinetics equations would be valid for short time scale problems. Intermediate timescale problems like hours to days, those kind of end up being impacted by the buildup of fission products and the neutron absorbers that get formed from these fission products. Um, if we can account for the buildup of fission products, then the point reactor kinetics would still be relatively valid. But over a long time, problems like days to months, the point reactor kinetics are going to kind of not be as useful for us because over those timescales, our fuel composition is changing enough that we really need other calculations to be able to monitor the depletion and the buildup of our different fission products throughout the reactor. And so the kind of fission products and their production and their destruction is something that we'll talk about a little bit more in detail once we get over exam 2. So getting back to the point kinetics equations, these are going to be our main tool for understanding time dependence, at least in like the short and intermediate time. And so these are the equations, and we're going to start analyzing them in a case where the reactor was initially critical. And we're going to assume that all of these other like terms that aren't the number density or the precursor density, we're going to assume that those are all constant. So we have constant coefficients, and we're going to assume that this reactivity rho is a reactivity insertion that is initially zero because we're initially critical at time zero. And then after time zero, we're going to assume that this reactivity insertion is some value rho zero. And it could be positive, it could be negative. We're just saying that basically the reactivity insertion is a constant after the initiating event where the reactor was initially critical. And we're going to ignore sources. So this S total, that kind of total source term is going to go away. We're trying to analyze, see how the system responds to certain events in the absence of any sources. And these are assumptions that are relatively accurate for a lot of important cases of interest. So we want to be able to understand these. And under these assumptions, the point reactor kinetics equations, they were I plus one coupled first order different ordinary differential equations before, but now they're that and they have constant coefficients. So this is what our equations become, where we've just canceled out the total source term. And these are both time-dependent differential equations, which means that if we want to solve them, we need to know something about the initial conditions of the neutron density and of all of our precursor densities. We're going to assume that we know what the initial neutron density is, and then we're going to assume that the reactor is critical, which means that at time zero, if we're critical, it means we're kind of like in a state of equilibrium. It means that our neutron population isn't changing with time. And it also means that our precursor densities aren't changing with time. So if we're critical, then that means that both of these quantities are going to be equal to zero. The derivative of my neutron density at time zero is zero, and the derivative with respect to time of my precursor densities at time zero would be zero. And if we make those assumptions, we can show that this implies that my initial where's my cursor? That this implies that my initial precursor concentrations would be this. And this is going to be a question that I give you on problem set 6. It's a very easy one. If we kind of plug in what we just like, imagine that we're taking these equations and we're evaluating them at zero. So that means everywhere we see a t, we're plugging in zero. So if we look at this equation right here, if at t0 we assumed initially critical, so that means that this derivative is zero. Here we're evaluating the neutron density at time zero, which we know is just n naught. So we basically have 0 equals beta I times n naught over big lambda minus lambda I times the concentrations evaluated at 0. And if we take that equation and then move everything over to get the concentration by itself, we're going to like take this term, move it to that side, divide out the lambda, and that's how we would get right here. So like it's a relatively straightforward derivation. If you make these assumptions, plug everything in, and get that precursor density by itself to show that this is what our initial concentration of our precursors would be. And then we have a complete problem because we have our differential equations and we have our initial conditions for the variables that we're solving for. So this is like that full problem statement where we're writing the neutron density and its initial condition. We're writing the precursor density equations and their corresponding initial conditions. Notice that for every Ci, you're going to write an equation for this precursor density. And for every Ci, you're also going to have an initial concentration that would be like C1 of 0 would be beta 1 and not over big lambda times lambda 1. And you would have a similar formation for I equals 2 and 3 and 4 all the way up to big I. And so now that we have a complete problem statement, we can try to begin solving for these different, for the number density and also for the different precursor densities. So we have a case where it's a homogeneous problem because there's no source term, and we have coupled ordinary differential equations with constant coefficients. So if we recall back to our good old math days, we can remember or recall or look in our books to remember that in this case the solutions to the variables that we're solving for are just a sum of a sum of exponentials. So this is basically going to look like a sum of quantity I plus 1 exponentials, meaning that's going to look like some a times e to the b times t. And then you'll have like a bi for every different for every depending on how many groups you have, you'll have a certain number of these exponentials that make up your solution. And whenever we write this out, though, these are going to be the general form for each of these solutions. And these exponentials, the time constants in the exponential are always going to be the same for every different function that we're trying to find. So the time constants, these little bi's, are going to be the same as the time constants in the other functions. So if we were to write the general solution, it's going to look like a sum of these exponentials. Each of those exponentials is going to have a different time constant. But if I compare the solutions for n total, or C1, or C2, or C3, all of those time constants for each function are going to be the same. So if we kind of take that and we generalize it, then the total neutron density, the solution is going to look like a sum going from k equals 0 all the way up to big I, and then we're going to have an a sub k times e to the omega k times t. This approach of the sum means that we end up with I plus 1 terms because we're starting at 0. So k would go from 0 all the way up to big I. So like if I was 3, then you would have 0, 1, 2, 3, which means you would have four terms in total, I plus 1. And similarly for the CI, it's going to look like a sum, also going from k equals 0 to big I. Um, the coefficients up front for each solution will be different. So for this, I'm going to say BK. And for each precursor type, there's going to be a different BK. So the constant up front, the multiplicative constant up front are going to be different from each type, from each function that we're solving for, but the exponentials are going to be the same. So this is going to look also like e to the omega k times t. So that's kind of like what I was trying to say whenever I was saying that these exponentials are the same as the time constants that appear in the other functions. I'm saying these omega k's are the exact same as these omega k's. And this choice of indexing is how we go from 0 up to I, which gives us a total of I plus 1 total terms. So that's kind of point one, is just remembering that for the kind of equations that we have, these are the general solutions. It's going to look like a sum of exponentials. And we know that these exponentials are going to be kind of governed by what these time constants are. Like if these time constants are positive, then our solutions are going to look like exponentially increasing functions. If these constants are negative, then they're going to look like exponentially decreasing functions. And the size of those time constants, like if they're very, very large or very, very negative, is going to influence how fast our solution would like blow up to infinity or drop down to 0. So we want to ultimately know more about those time constants. Um, it's helpful to recognize that if we take these equations, they kind of are well suited for a matrix form of solving, where if we were to write this equation out, this first equation is going to be this first line in my matrix, where the first coefficient, the way that I've set up my solution vector is that it's n of t, and then all of my different concentrations going from C1 all the way up to Ci. So if I were to write out this first equation, the term on the left side is the derivative with respect to time of my neutron density. The coefficient attached to n total is rho 0 minus beta over big lambda. And then because I have a sum here, I'm going to have a bunch of terms that look like lambda 1 times C1 plus lambda 2 times C2 plus lambda 3 times C3. So that's kind of what, like this lambda here would be multiplied by this C1, this lambda 2 would be multiplied by this C2, all the way up to this lambda I would be multiplied by CI. So this first, oops. So this first line is this first equation. And then I have capital I numbers of precursor density equations. So this line right here corresponds to my density equation for group 1. So I've got a C1, I've got the derivative of C1 with respect to time. I've got a beta 1 over big lambda being multiplied by the n total, which would be like this guy right here, this guy right here. And then I am only writing I equals 1 for the first equation. So then the next term would be negative lambda 1 times C1. So I have a negative lambda 1 right here. And then every other term is zero because that is multiplied by C1, and then I don't have any other terms for the C1 equation. And then I could go ahead and I could write my equation for C2, which is only going to contain a negative lambda 2 C2. C3 is going to only contain a negative lambda 3 times C3, and I get this kind of shape of my coefficient matrix that gets attached to my solution matrix. So helpful to just kind of see this in matrix form to hopefully make it easier to see, like spelling out all of the equations, why this is a total of I plus one equations, because we have one equation for the neutron density and then capital I equations for the precursor densities, giving us I plus one equations in total. And if we can recognize it's in a matrix form, it can help us with the solving process. So in general, our solutions are going to look like something, some exponential, some e to the omega t. And so if we were to take these definitions, notice that if this is the form of my solution, we can get analytical expressions for those derivatives, right? We can take derivatives of exponentials. If I take the derivative of e to the omega t with respect to time, what is that going to look like? Perfect. It's the derivative of an exponential is just itself. So we get an e to the omega t. And then when we do this derivative, we have to then do a product rule and take the or chain rule. We have to take the derivative of the inside, and the derivative of the inside is just omega. So that's why Ravi was saying it would be omega times e to the omega t. And then for the densities, it's going to be the same. We're assuming it's the same functional form. So the derivative of that is also going to look like an omega times e to the omega t. And so if we know this is the form of our derivatives, then we can just plug those into our equation. And we just want to recognize that e to the omega t, that was the original solution. So I could say that this is the same thing as omega times n total of t, because e to the omega t is in total. And I could write the same thing for my density. I could say that this is omega times ci of t. So if I take these definitions for my derivatives and I plug them into equation one, and I take this definition and I plug it into equation two, then that's what my left side looks like. From there, I'm gonna take all of my terms and move them over to one side so that I get like a equation where the right-hand side is equal to zero. And if I write my equations like this, and I put them in a matrix form, then it's going to look like what I have here, where basically every single term is going to, and every term along the diagonal is going to end up with an omega subtracted off of it because of this first term here, and also because of this term here. So down the diagonal, it basically looks just like what I had before, except down the diagonal, I'm subtracting off an omega term. So this is the matrix form. And ultimately, we want to find non-trivial solutions to this system. And if we want to find non-trivial solutions from like our linear algebra, our fond happy times in linear algebra, we know that if we take the determinant of this coefficient matrix and set it equal to zero, that is what will force this system to have non-trivial solutions. So it's going to have non-trivial solutions if the determinant of the coefficient matrix is equal to zero. And I guess what we're saying is that this thing right here, this is like our coefficient matrix, which is a size of I plus 1 by I plus 1. And if I take this coefficient matrix and I multiply by my solution vector, where I could say just x for my solution, which is an I plus 1 sized column vector, that those two things being matrix multiplied together equals the zero vector that also has I plus 1 elements. So this thing right here is the coefficient matrix that I'm talking about. So we want the determinant. We're saying that we want the determinant of that a I plus 1, I plus 1 to be 0. Take the determinant of that big coefficient matrix and set it to 0. So if we set that determinant equal to 0, we're going to get an I plus 1 order algebraic equation that contains our time constants. So ultimately, that was what I was trying to say, is that we're going to take the determinant of that big coefficient matrix and we're going to set it equal to 0. And unfortunately, if the number of groups is greater than 2, then you can't really do this analytically. At least you can't do it very. It's not fun. It's not simple to do it analytically. To find ultimately, we're trying to find what these omega values would be. So instead, if the groups is more than 2, you kind of want to do numerical solving for it. But what we can do instead is we have like another approach that we could use to find what these time constants are. So ultimately, what we're going to do is we're going to take these equations like after we substitute it in that exponential form, but before we put it in matrix form, we're going to kind of do a different approach, which is that we're going to notice that in equation 2, we could get Ci of t by itself. We're going to take equation 2 and isolate Ci of t. And then we're going to take that formula for Ci of t equals stuff, and we're going to plug it in right here into equation 1, which will eliminate Ci from equation 1, and it'll give us a new version of equation 1 that every term has a multiple of n total attached to it. And if every term has an n total attached to it, we can actually go ahead and just divide out the n total, because the only way that would be bad is if n total was 0, but we don't care about the non-trivial. We want the non-trivial solutions, so we can ignore the 0 solution. And then that resulting equation, the n total will be gone, and we can just algebraically isolate the row 0. We can just move everything else to the other side to get row 0 by itself. And then we're going to end up with, in this summation, we're going to have a bunch of sums of our beta i's. And we can just use the definition that the sum of those beta i's is the effective delayed neutron fraction, beta with the overbar on top. And if we do that, the result that we get is going to look like this. It's going to look like row 0 equals omega times big lambda plus a sum that goes from I equals 1 all the way up to big I. And we're going to have an omega times a beta I over the quantity omega plus lambda I. So if we go through that process, this is the equation that we end up with that we can use to solve for those time constants. We can't solve it analytically, but we can solve it using like a computer, like using a graphing calculator or using a numerical solver. So that equation is going to be the one that we actually use to understand more about what those time constants are. So that equation right here, it has a name. This is called the n-hour equation. The n-hour equation. If you were to plot this solution out, depending on how many precursor groups you used, like if you use capital I precursor groups, then what you're going to find is that if you plot this thing out, it's going to almost look like a wiggly, like an arctan function, but it's going to have like a bunch of repeating parts. And there's going to be exactly I plus 1 places where that function crosses the like horizontal axis. And so those correspond to the roots of the equation. And so the best way to solve this is to just like use a graphing calculator to plot what this function looks like, and then to find the individual zeros, which will correspond to those time constants. And that's how you can find those time constants, and then that's how you would know what the solution form of your of the n total and of the Ci would look like. So if all of our exponentials look like e to the omega k times t, if t is in seconds, what are the unit, or if t is just in time units in general, what do the units of omega k have to be? Inverse time, right? These have to be units of inverse time. So like if t is in seconds, then these omega k's are going to be in units of inverse seconds. And that's where the name comes from, right? In hour comes from the fact that in the good old days, they were using hours to talk about the time scales. So then these constants had units of inverse hours. Um, and ultimately, it's the sign of these time constants that's going to be really important to us because if these time constants are positive, then we're going to have a positively increasing behavior. If these time constants are negative, then we're going to have an exponentially decreasing behavior. And if the time constants were zero, then we would have e to the zero, which is nothing is changing with time. You just have a constant. So this is kind of what I was trying to describe when I was saying it looks like a weird kind of like a inverse tan kind of function. So if you were to plot this in our equation, this is what it would look like. Where the solid black lines is kind of like the right-hand side of the equation. And when you plot the inverse hour equation, you're finding the roots, you're finding where it crosses some horizontal line. And that horizontal line is going to correspond to the value of rho zero. So rho zero is just a constant on this graph. It's a graph of my inverse hour equation on the vertical axis. And it's a graph of, this is supposed to be omega on the horizontal axis. And that rho zero would be these horizontal lines. And this corresponds to a rho zero that is positive because it's above the x-axis. And then this line would correspond to a rho zero that is negative because the rho zero is below the x-axis. Positive, negative. So if you notice from the graph, there are a bunch of places where the inverse hour equation crosses these horizontal lines. And it doesn't matter if I'm looking at the positive case or the negative case. Notice that because I have I plus one, because I have I groups, I have I plus one exponentials. So I have a root corresponding to omega zero, and I have a root for omega one, omega two, three, four, five, and six. So in this case, I'm using six delayed neutron precursor groups. That gives me six plus one, seven exponentials. And notice that capital I of these exponentials, these six and these six, are always negative. So I of these exponentials are of these I of these time constants are always negative. And also notice that there's so remember this horizontal axis is the omega axis. So this would be the omega value where I'm crossing this line, where I'm crossing through the reactivity insertion, and corresponding. So each of these, we're talking about like this location on the graph. That would be the each corresponding omega value. And these horizontal kind of like asymptotes are corresponding to the decay constants for each group. So notice that if I look at negative lambda 1, that kind of bounds where all of these other omega solutions end up, right? That if this is my lambda 1, all I of these omegas are going to be, they're negative, but they're also going to be less than negative lambda 1. So they're negative and less than that minimum lambda, which is lambda 1. And then there's always going to be one of them that is, if omega zero is positive, then this time constant omega zero is going to be positive. If rho zero is negative, then this omega zero is going to be negative. But either way, this last time constant, omega zero, is always going to be the algebraically largest time constant, and it's always going to have the same sign as the reactivity insertion. So this last omega zero has the same sign as that reactivity insertion rho naught. That when rho naught was positive, this intersection point is at a positive omega value. If rho zero was negative, then this intersection point is at a negative omega value. And if the, the horizontal line here corresponds to rho equals zero. And when rho equals zero, this omega zero is zero. So in that sense, it has the same sign. It's either positive or negative or zero if the reactivity insertion is zero. So yeah, if rho equals zero, then omega zero is zero. And if the reactivity insertion was negative, then omega zero is negative. But it's still closer to zero than all of the other time constants that I would get. So it's negative, but closer to zero than the other omega values. And we can also say that if it's negative, then omega 1, sorry, if it's negative, then omega 0 is going to be bounded between 0 and negative lambda 1. So omega 0 is going to be between negative lambda 1, sorry, negative lambda 1 and 0. It's trying to say that it's going to be kind of in between negative lambda 1 and 0 if the reactivity insertion was negative. So we're always going to find omega 0 kind of in between 0 and negative lambda 1 if this insertion is negative. And this is being written in a very generic way, but it's always going to hold true in terms of the sign of the insertion telling me about the sign of all of these exponentials. So if the insertion's positive, one of these constants is going to be positive, all of the other ones are going to be negative. If the insertion is negative, all of them are going to be all of these constants are going to be negative, but the omega zero constant is going to be like the least negative or the algebraically largest. So when we solve that equation, I of those constants is always going to be negative. The other one, omega zero, is the largest algebraically. It's real and has whatever sign omega zero has. If omega zero, sorry, if rho zero is less than zero, if rho zero is negative, then omega zero is never more negative than that negative lambda one. And that lambda one corresponds to my minimum decay constant for my precursors. And that's going to correspond to the ones that have the shortest decay constants. And in our case, that if we're talking about uranium 235 fuel, it's going to correspond to bromine 87. Bromine 87 has a half-life of about 55 seconds. So that means that the lambda minimum for uranium 235 fuel is going to look like ln of 2 over that 55 seconds. And if you work that out, ln of 2 is like about 2 point something. So this is going to end up working out to be 1 over 80. And then it's going to have units of inverse seconds. So that lambda minimum is about 1 over 80 inverse seconds. And we'll talk about a little bit more about what that means in a moment. So kind of with all of that spelled out and that kind of introductory understanding of the fact that whatever the reactivity insertion is affects the sign of those exponentials, the sign of those constants that end up inside of the exponentials, we can use that understanding to start talking about and thinking about how does the reactivity insertion, how will my reactor behavior evolve based on various reactivity insertions. So if that reactor goes subcritical, then that means that the insertion is negative. And that means that all of my time constants are going to be negative. And so if we keep omega zero being the algebraically largest one, or the one that's closest to zero, then all of those other exponentials are going to be even more negative than omega zero. Like just as an example, maybe we end up with e to the negative t and e to the negative 3t and e to the negative 5t, and we go all the way up to like e to the negative, I don't know, 13t. So in this case, this time constant is -1. This would be the algebraically largest of all of these time constants, whereas this one would be -13. So that would be like the most negative or the algebraically smallest time constant. And so if I compare e to the negative t to e to the negative 13t, as time gets very, very large, which of these is going to go to zero fastest? The e to the negative 13t or the e to the negative t? It's going to be whichever ones have the most negative time constant. So the time constant that's the most negative is going to go to zero faster as I let t get very, very large. You could just play around with this, like even just like in a graphing calculator, and just imagine like evaluating these at like t equals 100 or t equals 1,000. What you're going to see is that if you compare the outputs of all of these functions, the one with the algebraically largest time constant is going to be the one that kind of stays around for the longest. And all of the ones that have that have more negative time constants are going to decay to zero faster. So in this case, this is going to just end up being dominated by that omega zero time constant. That time constant was negative, and it's going to end up um, the end behavior of my solution that contains all of these different exponentials, it's going to be dominated by the one that has the largest time constant because all of the other exponentials are going to end up decaying away to zero before this one. So what this helps us see is that this governing behavior looks like a negative exponential, and that hopefully makes sense that what we're saying is that if there's no source and we have a subcritical system, then the neutron population eventually exponentially decreases with time. It eventually exponentially decreases with time. And that should make sense because we're saying all of them are negative. So if my solution is the sum of all of these negative exponentials, and I look at that function, it's going to very quickly drop to zero. The end behavior is going to be dictated by the one that's the largest or the algebraically largest time constant. And that's why we say here that even though it's going to be dominated, the like kind of longer term behavior is going to be dominated by this guy. At the very beginning of that transient, the system might decay even faster than just this omega zero exponential does, because our solution is going to contain all of these negative exponentials that are going to decay way faster than the algebraically largest one does. So, and notice that that agrees with kind of what we had said about time-dependent populations, like from the very beginning of class. Like even when we looked at the behavior of a one group or an infinite homogeneous reactor, when we said that the system was subcritical, it meant that the e to the lambda t was negative, and that meant that the system exponentially decayed with time. So this agrees with what we had said before, but it also helps us to kind of understand more about this particular shape and form of those solutions, depending on how many precursor groups I have. So if it was subcritical, that meant the reactivity insertion was negative, and it meant that our omega zero was kind of bounded between negative lambda 1 and 0. And we already said that that lambda minimum is about 1 over 80 seconds. So if that time constant omega zero is like around that value, that means that that long-term behavior is going to be dominated by omega zero, which is going to look kind of like lambda minimum, which means that that 1 over 80 is going to be kind of like what my time constant looks like. And that means that if my solution looks like E to the negative 1 over 80 t, then it means that after 80 seconds, if I plug in an 80 for t, then after 80 seconds, my initial population would be decreased by a factor of e. So that's kind of like giving me an idea about if I were to look at a plot of my neutron density or my power or my scalar flux, and I wanted to try to predict over the first 80 seconds, what does that population do? If the omega zero is negative, then it's you could make the good like it's a good approximation to say that after the first 80 seconds, whatever that initial value is would be reduced by a factor of e in those 80 seconds. And that's just like a good kind of way that you could do like a hand calculation, but you just want to keep in mind that this isn't the omega zero isn't the only exponential in my solution, that I'm going to have a bunch of more negative exponentials than omega zero, which would make my population change and decrease faster at the very beginning as those more negative exponentials are decaying away. So now we want to talk about supercritical. And what we said with supercritical, with rho being positive, is that only one of those time constants, the omega zero, was positive, and all of the other ones were negative. So that means that my solution for n of t, maybe it looks like e to the 3t plus e to the negative t plus e to the negative 2t plus e to the negative 5t plus dot, dot, dot. We're basically saying I have one positive exponential and all of the other exponentials are negative. So if I were to ask the question, what does this function look like as t gets very large? As t gets very large, these negative exponentials are all going to decay to zero. So as t moves forward, the negative exponentials go away, and then my solution form over a long time period gets dominated by whichever one is the only positive exponential. And that corresponds to my algebraically largest one, which is the omega zero. So if it's a supercritical system, then my over a long time period, my solution is going to just end up looking like e to the omega t, where that was a positive omega zero. So therefore, if I have a supercritical system with no external sources, then as time moves forward, the system is eventually going to exponentially increase with time. So we're going to have increases exponentially with time. So that's kind of like the longer term behavior based on a supercritical system. And notice that at the beginning, these negative exponentials are going to start decaying away. So at the early part of this transient, it might decrease or maybe even increase a little bit, but it's eventually going to look just like this single exponential, which is dominated by the only positive time constant. And then if we consider a reactor that's critical, and then rho zero is zero, then that means that omega zero is going to be zero. So our n of t is going to look like e to the zero plus e to the negative t. And I'm just like kind of throwing in random numbers just to kind of illustrate what this is going to look like. Um, just making the point that all of these are negative exponentials except for the first one. So like if rho zero is zero, then that first exponential constant is going to be zero. All of the other ones are going to be negative. So if I ask the question for this critical system with rho zero being zero, what's the end behavior as t gets very, very large? Well, as t gets large, all of these negative exponentials are going to decay away. And all I'm going to be left with is this first one, which is e to the zero, which doesn't change with time. So as t gets very, very big, this is going to approach a constant. And therefore, what we're saying is that if there's no source and we're critical, then the system is eventually going to reach a steady state. Reaches a steady state. And that's how we define a critical reactor. It's a reactor that's able to sustain a neutron population where the gains and the losses are balanced. So this hopefully makes sense. And notice that what we're saying is that on the way to steady state, there might be deviations because of all these negative exponentials decaying away, but the longer term behavior is going to be dictated by that first one, the algebraically largest time constant. Um, so yeah, even if you have a source-free critical reactor, it might change a little bit before it eventually settles into that steady state as those negative exponentials decay away. And this is a nice plot that kind of just illustrates like if my the quantity of interest, which in this case is the reactor power, and we're going to talk a little bit more about this in the upcoming, you also see this on the homework, but basically when you write those point kinetics equations, we write them in terms of the neutron density, but you can convert the neutron density into a flux by multiplying by the neutron speed. And if you can convert that neutron density into a flux, well, you can convert the flux into a power by multiplying by E sub f and by sigma f. So in that sense, you can add multipliers onto the terms in the kinetics equations to talk about the evolution of things besides the neutron density. And they will all have similar forms because all you're doing when going from one to another is just multiplying by certain constants. So this is showing what the power, the kind of the normalized power looks like. But you could think of this as the same thing as just saying n of t over my initial n naught. So initially it's at 1, and then this is showing how the system responds to various changes in the to various reactivity insertions. So if rho 0 is negative, that means I'm subcritical, and that's this downward line where it kind of drops really quick at the beginning, and then all of my exponential time constants are 0, or sorry, are negative. So as time goes forward, it kind of just looks like a single decaying exponential when my insertion was negative. This one right here is saying that my insertion is positive, but my insertion is kind of bounded between 0 and the delayed neutron fraction. So that's what this one is showing, where it kind of sort of more slowly increases at the beginning, and then we have exponential increase as the result of that one time constant being positive remaining in the system. And at that point, all of the negative ones have kind of decayed away. So my end behavior just kind of gets governed by that one positive increasing exponential. And then the rho 0 greater than beta, that's this line right here. And that's basically something we'll talk about a little bit more in as we move forward. But basically, if you make that insertion be larger than beta, then your population just kind of does a really something called prompt critical, where it just kind of shoots up to infinity, um, at least in the short term. Um, so yeah, this is kind of like if you were to actually plot the solutions to these. So if you were to plot the solutions to the point kinetics equations, knowing what those exponentials are, these are kind of like what the end behavior of those functions that you would see. And that kind of agrees with this plot that we had shown here. So this plot is kind of confusing, but it's important to kind of internalize it because it kind of holds the keys to understanding based on different reactivity insertions, what do these exponentials look like? And based on what those exponentials look like, that's going to influence our end behavior. So yeah, that was everything I had for y'all today. When we come back next time, we'll talk more about transients and feedback. And yeah, so if y'all have any questions at this point, feel free to let me know. If not, stick around because I'm going to pass back your exams.